Hello everyone, I'm John Martinez. You're watching Learn Together Filmmaking. Today we're going to be talking about how to build this hexagonal grid that sort of disappears on its own whenever something gets close to it and then is able to reappear behind anything that gets close to it. You can use this for creating a sort of futuristic sci-fi door or wall that just people can walk through but looks like it's there until they get close to it. And it is, of course, as all things geometry nodes are, completely procedural. We can make this grid bigger or smaller as we want to, or change the resolution, if you will, of these hexagons that we're using to create everything. We can even change how sensitive our little exclusion zone is for this as well. We can make it go closer or farther away, give it more sensitivity to everything around it. And of course, you can select different objects if you want to, or even set it to a collection if you want to have multiple objects interact with it at the same time. So let's go ahead and get into it. All right, here we are in our new project, and we're going to go ahead and head on over to the Geometry Nodes tab, and we're going to create a new Geometry Node setup for this cube. First thing we're going to do is configure our group input so that we can alter this procedurally. So we're going to go into our group tab right here. We're going to remove this geometry input right here because we're not going to be using this original cube shape. And what we're going to do is go ahead and create 4 inputs. We're going to name them grid size, leave that as a float, then grid density or resolution, if you will, depending on how you want to what you want to call that. We're going to change this one to an integer. Then the next one, going to leave it a float, call that proximity sensitivity. And the last one will be proximity object. This, we're going to change this to be an object, or if you're planning on having multiple objects interacting with it, you might choose a collection and then put all the different objects into your collection. For this one, though, we're just going to leave it as a single object. Now that that is set up, we are going to start getting into the actual creation. So the way we're going to do this is by creating a grid in which we're going to overlay some hexagons on top of it through the use of instances. So let's go ahead and create our initial grid. So the first thing we're going to do is connect our grid density to our number of vertices right here, and connect that on over to our group output. So as we are already right here, you can see we're procedurally determining the number of vertices that we have within our grid. And for what we're initially going to do is also connect our grid size here, do the similar thing. And there we go. We have initially created our initial grid right here that we're going to use. Now, if you have a hexagonal grid, what you cannot do is have the grid be straight lines like this in both directions. So within any given row, you may have a hexagon like that, and then have the next one touching it on the corner right here like that. But if you have the next row of hexagons lining up exactly perpendicular to this one as well, you're going to end up with something that looks a little bit like that. And when you do that, then your hexagonal grid is going to have a big empty space right here, which you don't want. So the way that you actually solve this problem is, first of all, by rotating your hexagons. If I can learn to draw something like that, and then actually starting the next row of hexagons slightly offset to the first row like that. So essentially the points have to go in a pattern like this, and then along this row it can remain flat, but we need to alternate the displacement of each row along this axis, the y-axis. So how do we do that? How do we create the displaced rows that alternate back and forth between position 1 and position 2, essentially? Well, we are going to use a little bit of math and some trigonometry. So first, we'll go ahead and create a set position, because this is what we will use to actually create the displacement itself. And then we are going to create a a math node and a position attribute for which we want to create a separate XYZ. Go ahead and connect that right there. And what we want to do is use the Y position, that is the position along this axis. We want to use that to determine whether or not this point is going to be displaced along the x-axis. So the way we're going to do that is by taking our Y position right here and putting that through our math node, and then going to a combine XYZ and using that into the X position right here. So in other words, we're going to take the position of any given point along its Y axis, run that through a math function, and then use that to change or not change our X position. So we're going to go ahead and connect that right there, and it looks weird. So we need to use our trigonometry here. So if you have done any trigonometry functions before, you know that sine and cosine are going to be the two options that we're going to be looking at, because they are a regularly repeating oscillating function like this. But which one do we choose? Well, that's going to be determined by the position of each point along our grid here. Let's go ahead and just choose one. Let's see what happens if we choose, say, a cosine. Well, we start to get something. We're getting a curve. It's not necessarily the right curve, but it's getting there. And if we, say, increase this a lot and make it a really big grid and bump up the resolution, you can see how we're getting this oscillating pattern right here. So what we want to do is basically space out our vertices so that we have one vertex right here, one vertex right here, and there, and so on and so forth, and nothing in between, nothing in this area right there. That way, each vertex is going to essentially be alternating between this position, that one, and then so on and so forth. And the way we're going to do that is by, first of all, changing this so that our grid size is actually, the actual size right here within the grid node is not actually based off of our grid size input. We actually want it to be based off of the density. The reason we want to do that is because this function right here, where we actually have each one based off of that, only works if our size is one less than the integer that we use for our vertices. And that will become apparent in a second once I go ahead and set it up for you. So we're going to take a subtract our grid density. We're going to subtract 1 from that and then replace our grid size right there. And it still looks really, really weird. The way that we're actually going to fix that is by taking our Y position and taking another math node. And what we're going to do here is multiply it by pi. Now, if we zoom in now so that we can actually see, we can see that it's actually working. It's going so that here's one vertex, and then the next vertex is going to be pushed in a little bit, then another vertex, and then so on and so forth. So it works, and we now have a setup where no matter what number we put in here, it's always going to be functioning exactly as we intend for the alternating pattern in here. Except for one thing. If we put in an even number, you can see that it goes back to a square. And why is that? If you look at this cosine graph, you can see that when x is 0, y is 1. What this means for our situation is, since we are rotated and we're modifying it along the x-axis, when the y position of a given vertex is 0, the x position is going to be displaced by 1, which you can see right here. When our y position is 0, our x position is going to be right there. And then if we unmute this, then you can see that it gets displaced over by 1 in the x direction. And then when we get over to our minimum, essentially right here, it gets displaced by 1 in the opposite direction. Now, the reason we have to use this multiply node here with the value of pi is because the period of a cosine function, that is the distance from here to here when you're not using this, from here to here, that is 2 pi, or approximately 6.2. So we can count that out. 1, 2, 3, 4, 5, 6. It's roughly 6 from one peak to another. And since we have our vertices spaced evenly one value apart, we want to compress that so that rather than the distance being 2 pi, we want it to just be 2. We want to compress it from here all the way to right here. And the way you do that is by multiplying our y position by pi. What that does, it essentially says when it's going through the cosine function, it's saying, oh, this isn't really here at 2, it's actually all the way at 2 pi. It's just a math conversion right there that isn't really particularly necessary for you to know. It's just a little bit of information there. Anyways, now we have a function that is set up evenly, but it still doesn't work when the value is an even number, and that's because now we're not dealing with vertices that are on 0, 1, 2, and so on and so forth. We're dealing with vertices that are on half, 1.5, 2.5, which that is when we actually need to use a sine function. Now, if you see when we switch this to a sine function, we're actually able to maintain that right there. So how do we get it so that we can use any grid density and still maintain our oscillations right there? Because now if we're on sine and we switch it to an 11, that is an odd number, then it no longer works. It's a square again. So we have to switch it back to a cosine. Well, the way we're going to do that is by taking our little setup right here that we've created. We're going to set up a Boolean function that allows us to switch between sine and cosine depending on whether or not the number is odd or even. So I'm going to fast forward a bit and clean this up and get back to you in a second. Now that we're here, we can start setting up a Boolean function to determine whether or not a number is odd or even, and then use that to switch between a cosine and sine function. So the way that we're going to do that is by using a compare floats node and another math node. And we're going to take our grid density and we're going to set that to a modulo. Now what a modulo does is it takes the top value and divides it by the bottom value and then outputs the remainder of that. That is the decimal places that happen after that. The way you can test for an even number is by dividing by 2. So if it's an even number, that is the grid density is say 10, it's going to go in here, take 10, divide it by 2, and then that equals 5, exactly 5. And so the remainder then is going to be 0. But if we take an odd number like 11, we take that, divide by 2, that's going to be 5.5. So what this is going to do is going to output that half right there. And that's where this compare floats comes into play. For every odd number, we know that it's going to have a value of 0.5. And for every even number, we know it's going to be 0. So we can use that to create a Boolean that essentially says, yes, a number is odd, or yes, the number is even. And then we can take that and use a switch node. So by using a switch node, we can take the result of our Boolean right here, that is true or false, and then take two different geometries right here. You can take a geometry for cosine and a geometry for sine, and then it'll switch between the two based on whether or not this outputs a true or false for a number being odd or even. Let's go ahead and connect that right there. Switch this one to a sine and this one to a cosine. So right now we are currently at 10, and so therefore it is an even number. This outputs a 0. This modulo outputs a 0, which is not greater than 0. So therefore the result is false. So it outputs a false result, which comes to our switch. And the switch says it's a false result. So it takes this right here, this top group going into the false input, which is a sine value, which as we know works for an even number for the grid density, and outputs that as our geometry. Then if we switch it to a 9 or any odd number for that matter, this outputs a 0.5, which is greater than 0, so the result is true, and it selects this geometry down here. And that is how you can build an an even odd detecting switch that allows you to select between a sine or cosine function so that you can have any number of vertices that will continue to oscillate. That essentially builds our grid. Let me go ahead and frame this up. All right, so also one thing we need to do before we move on to the next section is to change the amplitude of these oscillations, because right now the difference between this side and this side is 2 units along the x-axis, but what we want is for it to only be 1 unit along the x-axis. We'd rather it only be this much. And the way we're going to do that is by adding in another math node. We're going to take a multiply add node. And what this is going to do is allow us to multiply by 0.25. Then what I'd like to do for our cosine section is to then subtract 0.25, just because I like to have this vertex right here be centered on this object rather than offset anywhere else. Like if it's slightly off center, I would rather it be centered like that. And then for our sine section, we're going to just use a multiply node, because that's going to get us about as close as we can get to center, because it'll center this along our center of our object. Not strictly necessary to do the multiply add anyways, just a personal preference. Now that we have that set up and everything is appropriately scaled, as you can see, if we go here, it's actually only going to be a ½ unit offset, which is actually what we want. We want a ½ unit offset because our hexagons need to be offset from each other by 1/2 of a hexagon so that they can kind of lock together in a way. So now we are going to create our instance objects on top of this, our hexagons. So let's create an instance node, which then makes everything disappear because we're not instancing anything at the moment. And a hexagon is nothing but a cylinder with exactly 6 vertices. So we'll do that, and it is not right because our hexagons are way too big and they're overlapping with each other quite a bit. So if we take a look at that, they're now lined up properly. They're roughly correct, but they're the wrong orientation. We need them to be rotated 30 degrees along the z-axis. So what we're going to do is take our rotation right here and go 30. So this way, the flat sides on this axis are going to line up so that we can then grow our hexagons until they line up and touch each other just a little bit. Now the exact number that you're going to want to choose here is 0.577, basically infinitely repeating sevens, but 3 sevens is close enough. The reason for this particular value is that the distance between any 2 hexagon centers is going to be exactly 1 meter. And the minor radius right here, that is the distance from the center to any of the flat sides, this minor radius right here is going to be given by this formula on the screen, which is defined relative to the major radius, that is the distance from the center to any of the vertices, given by capital R. And if you solve for this minor radius, which we know is exactly half of 1, so R equals 1/2 of a meter, then we can solve for the major radius, which is going to end up being exactly 0.5777, so on. Now that we have our hexagons scaled properly, you can see that we still end up with a bit of a gap between the hexagons going this way right here. And the way we can get rid of that is by taking our original grid right here and just kind of squishing it in a little bit along the y-axis. The way to do that, we can take a transform node, go ahead and plug this in before our instance node. Perfectly hexagonal grid with no overlap and exactly the right size. And this hexagonal grid is going to always get bigger based off of the number of vertices that we have here, which is what we want, because now we can take our grid size and then use that to scale this grid. And the important thing here is that each hexagon is going to be a uniform size no matter what the number of hexagons is. And then we can take our grid size and scale this entire thing by using another transform node. Plug that in right there. And then take our another group input. Take a combine XYZ because we only want to, with this grid size, we only want to scale it along the X and Y axes, not the Z axis. And for right now, we'll go ahead and change this number to a really small number so that it's more flat. So we only want to affect the X and Y axes. So our Z axis is going to be exactly 1. And then X and Y, we want that to be connected to our grid size. Now, if you do this, it makes our grid size or our grid get very, very large, which, you know, it doesn't particularly matter, but it's not easier. It's not easy to work with because then this has to be like a really small number for anything that you want to work with. And the solution I kind of found was just to take a math node, take our grid size and divide by the grid density. The important thing here is that actually our grid size is roughly reflective of real world size of the grid. That is, we have, if we put 2 in here, the width of it is going to be 2. It's not quite going to match along the y-axis because, again, of the scaling that we did before, but now the width of the grid matches whatever number we put in here in terms of meters. We know exactly how many meters wide this thing is going to be. So yeah, that gets us our hexagonal grid. We can change the resolution of our grid. We can change the size of it. And now to move on to the making it so that it is responsive to an object passing through it and will disappear as needed. All right, now to start making our disappearing portion of our grid. Go ahead and bump up the resolution and size a little bit to match what I had in the demo video and start working on this. So we will use another group input and we'll go ahead and create our object. I'll just use a torus and switch out of wireframe view because this is where it starts getting a little bit confusing to work with that. So we'll take our proximity object right here and select the torus. So now the object, the torus, is able to be passed through here. So we can use a little bit of object info. Take our object, pump it into there, and take a geometry proximity and use that to drive the rest of it. So I'll take our geometry, put it into the target. So now it's reading, this node is now reading the geometry, and then we are able to say output this data into a scale instances, because again, all of these hexagons are instances on a grid that we have created. Right now it's scaling by 1, so nothing changes. But if we take this, take the distance, that is the distance of any given face of our torus, it'll take the distance from that to every point, every instance on our grid. Take that and put that into a scale. And what that does is it makes things a little bit weird, but it's starting to get the right idea. You can see that the ones closest to it are really small. The ones farthest away actually got bigger, which we don't want them to get bigger. And we want to control this a little bit better than we are right now. So the way we're going to do that is by taking a math node and inserting that between the two of these, which just makes things even weirder. So we're going to go ahead and clamp it. So now it's only affecting the things closest to it, and it's not making anything bigger when it's farther away. But what we can't do right now is control with our proximity sensitivity. And the way we're going to do that is by changing this to a subtract and connect this through to there. So now, with that being the case, our proximity sensitivity is able to change this. It's essentially spreading the effect of this a little bit more. So that's how you get a difference on the proximity right there. But you'll notice if I move this, nothing changes. The way you fix that is by taking our object info right here and setting it to relative. Now, as I move this around, our our grid shrinks in response to it no matter where it goes. And what we'll go ahead and do is create a group for all of these things. It's, again, not strictly necessary, but just to help tidy things up a little bit. I like to have one single object for this, because this is an interesting thing that I might be able to say export into another project and use it for something similar, where I have something that shrinks in response to the proximity of something else. That's why I grouped it rather than framing it. All right, and we are almost done. Now, in order to put a material on this, we could just go over and create a set material. Go ahead and select this material and go on over to our viewport shading, and it will work more or less. Go ahead and switch on over to cycles, GPU, because I always use that. And hooray, we now have a material that we can apply on top of it and do whatever you want to with it. But say you want to create an image texture over this, like you're going to be using it for a VFX shot and you want to put a plate on top of it so that you will be able to key it out or overlay it on top of something, whatever it is. If we go over to the shader editor and create an image texture and load up, say something like, go to my desktop and say load in this picture right here. If we connect this to our surface, go and get rid of that, and use our texture coordinates, the only one that gives us any results is this one, the generated coordinates, but you'll see that it's creating an image over each individual hexagon. And the reason is because when the grid is when it's still instances, you can see in our spreadsheet here, there are no vertexes and only a bunch of instances. So what it's essentially doing is treating each individual hexagon as its own separate object, which we don't want to do. If we want to put an image texture over the entire thing, we want it to treat this entire thing as one object. And the way to do that is by realizing instances. We have to do this before our set material. So now it's treating this entire thing as one gigantic weird shaped thing with points and all that stuff. And you can see all of our vertices now show up over here. So if we go to our rendered view mode, it now looks right. It's one image for the entire thing. And as I bring this through, it is able to affect all of it. And if we want to, say, change this so that it is a little bit more correct, aspect-wise, it's a little bit squeezed. It's squeezed a little bit. We can just take our x-axis, because this is a 16:9 image that I originally had. So we can just take our x-axis and make it a little bit wider by a factor of exactly 9 divided by 16, and then translate it over to wherever we want it. And there we go. That's approximately correct. But the one bad thing about this is that if I wanted to use a different image, I'm going to have to adjust the values, figure out where I want this to be. It's just a little bit complex that way. So what we can do is, by using the technique that I discussed in my mountain tutorial footnote, to pass through our vector, our position vector coordinates from here, from the geometry nodes, into our shader editor. And the way we can do that is by capturing the attribute. Again, you have to place this at the very end, right here at the end of the chain. Set this to a vector. Then we can connect a position node attribute into there. Take this attribute, plug it into our output. Go ahead and name this to position vector, and then take our grid size, plug that in there, and make a size attribute. Now what we can do is refer to these both in our shader editor. So we're going to create an attribute node, put this one as position vector, and create another one for our size vector. And if we take our position vector and replace that one, you can see it gets all weird again. And the way we can fix that is by using our size right here, and go ahead and move that up there. If we just plug our size attribute directly into our scale, you can see it actually makes things a lot worse. And the reason for that is because we want to scale up each of these images, make them bigger. And the way to do that is by making these numbers along here smaller. So we can go ahead and take our size vector, and actually what we want to do is divide it by 1. And that allows us to scale things up almost to the right level, but not quite. It's almost there. But our x-axis, again, we're going to run into the same problem that we had before, where the x-axis, it's turning it into a square image, which we don't want. So we're going to take a combine XYZ and another math node and take this into that. Our y and z are going to be accurate as is. And then take this one and multiply by our number that we established before, our 9 divided by 16. That is our aspect ratio. And plug that into there. And now we can offset by 0.5 meters in each direction. And now we have a properly scaled and positioned image by using only the data from our geometry nodes. And you can choose any image you want to, put it in there, and now we have a fully functioning nano door, trademark pending. Well, that's everything I've got for you. I hope you enjoyed this video and find a way to use it in your own project, whether it be VFX work or animated. Let me know in the comments down below if you do, and I'll be sure to give you a shout out. I'm John Martinez, and this has been Learn Together Filmmaking.